Hi everyone. Before I start chapter 7, I added 5-page extra contents about chapter 6, and I'll explain the details of the added extra contents about chapter 6. The fourth thing I like to explain in detail is the kinetic energy by a constant force. I've already explained this in chapter 6, but I like to make sure that the basic concept of kinetic energy by a constant force. If there is a constant force, there will be constant acceleration, and the Newton's law states that F, the force, is equal to mass times acceleration. And if the acceleration is constant, then the velocity is the integral of acceleration, and if a is constant, then it becomes integral of constant becomes the constant times the time t. So we have v equals a times t if acceleration a is a constant, and the distance traveled by an object s is defined as the integral of velocity. So as the velocity is a times t, where a is the constant, then the integral of velocity becomes integral of t. So the integral of t with respect to t becomes 1 over 2 t squared. So the distance traveled by an object with a constant acceleration becomes 1 over 2 a times t squared, where a is a constant. By the definition of work is F times s, force times the distance. So force is ma, and the distance traveled by the object is 1 over 2 at squared. So it becomes 1 over 2 m times at squared. So at is equal to v over here, so I can replace at with v. So the work done on an object becomes 1 over 2 mv squared, and we define this as a kinetic energy on an object. If an object is moving with a velocity v, speed v, then the work done on the object is equal to 1 over 2 mv squared, and that is the kinetic energy. We have derived this before in chapter 6, but I like to explain this by the definition of force and the Newton's law, by the definition of velocity and the definition of distance with respect to the velocity. So that's the content I like to emphasize. Next, we have an example. As some students asked questions during the class, after the class I made this as an example. But there is a girl and she throws a ball at the height of her height, and the ball goes up, and at a peak of the ball it starts falling down, and it falls down to the ground. And when the height of this goal is 1.05 meter, then what would be the speed of this ball when it comes back to the initial position and when it falls down on the ground? That is the question. When the initial speed of the ball thrown by this goal is 10 meters per second. So the height of the goal is 1.05 meter, and the ball of mass 0.1 kilogram is thrown upward with initial velocity 10 meter per second. Then the first question is, what is the peak height h of the ball when the gravitational acceleration is 10 meter per sec square? The force by the gravitation is F is equal to mg. When it reaches the peak height, then it will stop and then it will start falling down from its peak position. And by the energy conservation law, we can have a simple equation, which is mgh. That is this is the work done by the gravitational force. As before, as we have just explained before, the work is just 4 times the distance. As there is a constant force, gravitational force downward, and as this ball travels by distance h, which is the peak height, that is equal to the kinetic energy at the initial point. So the kinetic energy at the initial point will equal to the work done by the gravitational force, that is mg, which is the gravitational force, times the distance h. So by this simple relation, we have h is equal to v0 square over 2g. When v0 is 10, we have 100 over 2 times 10. So that is 20. So we have h is equal to 5 meters. So when there is a gravitational force, it generate a work which is equal to the kinetic energy at the initial point, because the ball at the initial point has velocity v0, and its kinetic energy will be lost by the work done by the gravitational force, and it stops at the top, at the peak of the ball. That's where the velocity or speed becomes 0. So we have the simple relation like this. The work done by the gravitational force mgh is equal to the kinetic energy at the starting point. So we have the peak height as 5 meters. The second question is, what is the speed of this ball when it becomes back to its original initial position? This ball is thrown by the skull, and it will go to the peak position and it will go down to initial position. Then the question is, what is the ball at the initial position when it returns back from its peak position? By the energy conservation, the final speed should be equal to the initial speed. So we have 10 meters per second, but it's going downward in this case. And the third question is, what is the speed of the ball, Vf final speed, when it reaches the ground? When it reaches the ground, it will stop, but just before it hits the ground, what is the speed of this ball? Again, by the energy conservation law, we have the final kinetic energy minus the initial kinetic energy at this point is equal to mgl, when L is the height of this goal. So the height of this goal is 1.05 meter given by the problem. So the final velocity becomes the square root of 2gl. If I cancel the m on left side and right side, we have 1 over 2 Vf square minus 1 over 2 V0 square is equal to G times L. So if I summarize this, we have Vf equals to square root of 2GL plus V0 square. And G is 10 and L is 1.05, so 2GL becomes 21, and V0 square is 100. That is square root of 121, that is equal to 11. So the final velocity just before it hits the ground becomes 11 meters per second. That's the example I like to you or to understand by using the work done by the gravitational force, and the kinetic energy is the result of the work done by the gravitational force. This is the second example. The first example I'd like to show you related to the work and the kinetic energy. There was an example in chapter 6 about the varying force. So I like to summarize the kinetic energy by a varying force. Work by its definition is force times the distance. That is, when F changes with distance, it should be an integral of F with respect to ds, that's the displacement. And F is equal to ma by the Newton's law. If I rewrite a, that is dv over dt, that's the derivative of velocity, it becomes acceleration. So we can write that the work is m integral of dv over dt with ds. And if I replace dv with ds, then this becomes ds over dt times dv. So this is the product of dv and ds divided by dt. So if I replace dv, exchange dv with ds, then this becomes ds over dt times dv. But ds over dt is the definition of velocity. Distance, derivative of a distance with respect to time is nothing but the velocity. So we can rewrite this as m times the integral of v with respect to v. So v dv, integral of v with respect to v becomes 1 over 2 v squared. So we can write down as 1 over 2 m times v squared. That's the kinetic energy of an object. So we have, at the first page, we have derived that the kinetic energy when a acceleration a is constant, then we have 1 over 2 mv squared is the work done by the force. But even when the force is varying, not a constant, so a dv over dt, that's the acceleration a, is not a constant, but still the final velocity, if the final velocity is given, the work done by a varying force is still equal to 1 over 2 mv squared. So 1 over 2 mv squared is still same, even for a varying force. So that's the reason why it is called the kinetic energy of an object, regardless of varying force or constant force. And there was an example about a spring, and spring is a typical object which has a varying force with respect to distance of displacement. So spring is defined as an object which produces a force which is proportional to its displacement from its equilibrium position. So one of the most important characteristic property of a spring is F is equal to K times X, when X is displacement, and K is called a spring constant of a specific spring. So in this case, when we calculate the work done by the spring force, then we calculate work as the integral of force by the spring and the distance. Then, if I replace F as the K times A, K is the constant, so we can put K outside of this integral, and the integral becomes from x1 to x2, x dx. And integral x with respect x is 1 over 2x squared, so it becomes 1 over 2x2 squared minus x1 squared. That is the kinetic energy difference between two positions when an object is displaced from x1 to x2, and that is the work which is same as the work done by the spring. So this is an important property of a spring related to the work done by the spring. That is the formal explanation about the work done by a spring, and this will be equal to the kinetic energy difference between two positions, because the work by force on object of mass m will produce a kinetic energy. And there is an example about the work done by a curved path. When this is the first example, when there is a force and displacement is not parallel, we have a dot product of F dot ds. That is the work done by the force with a displacement s. So if there is a object on a slide, it is frictionless slide, then if an object is moved from one point to the other, when there is a gravitational force, we can calculate the work done by the gravitational force from this position to the other position. Then the work done by this gravitational force is F dot product with ds. F is mg sine theta. So if there is the force acting on this object along the vertical position, then this, because of the slide, we should decompose this force perpendicular to the slide and parallel to the slide. The parallel component of the slide becomes the F times sine theta when this is defined as the theta. So if theta becomes 0, then means this slide is the horizontal. That means there is no force along the side of the slide, and all force is acting to the vertical part of the slide. So the parallel force component along the moving direction of this object is mg sine theta, and the vertical force component is mg cosine theta. So if this object is moved from one point to the other, and if the height difference between one point to the other point is h, then this distance becomes h over sine theta, because sine theta is this distance, h over this distance. So this distance is nothing but h over sine theta. So if we multiply the force times the distance with this mg sine theta, that is the force acting on this object along the slide on moving direction of this object, and the distance traveled by from one point to the other is h over sine theta. So sine theta cancels out, and the work done by the gravitational force from one point to the other is nothing but mg, the force, times the height difference between these two positions. So the work done by the gravitational force from one point to the other, whose height difference is h, is just mgh. That is the same work done by the gravitational force for a free-falling object. So if this object is falling from one point to the other, whose height is h, then the work done by the gravitational force is just mgh. So regardless of the moving path from one point to the other, if the height difference is same, then it produced the same work, or it produced the same kinetic energy to the object. So that's the result or the work by the gravitational force. Actually, regardless of the path, if this object is moved from this point to this point, as long as the height difference is h, it doesn't matter whether it slides with a very different angle theta. It doesn't matter. Regardless of theta, it will produce the same work. If theta becomes 0, this is the situation for a free-falling object. If theta becomes 0, it will theta becomes 90 degrees, then it will just if theta becomes 90 degrees, it will become a free fall. So that's how it happens. So regardless of theta, as long as the h is same, it will produce the same work. That's the important property related to the work and the gravitational force. There is a final example about a pendulum. If a pendulum is an object is hung on a pendulum, and it can oscillate back and forth with an angle theta, and this is the pivot point. When the length of this pendulum is L, can we calculate the work done by the gravitational force when it starts from theta 0 and ends up theta equals 0? So when it falls down, then how will be the work done by the gravitational force for this pendulum? Once again, work is defined as force dot product with ds, and the force with the same analogy, if there is a gravitational force downward, mg, then the force acting on this object is mg sine theta. But I put negative sign because it is when theta is large, is positive, then the force is on the negative theta direction to decrease the theta. So I put minus sign, and the magnitude is mg sine theta. That's the force acting on this moving direction by the gravitational force mg. And the distance, small distance it moves is L times dl. This the circumference of this is circular motion, so circumference of this motion with respect to theta is just L times d theta, is the small displacement along the moving direction of this pendulum. So the only theta dependent is sine theta over here, and everything else is put outside of this integral. So we have minus mgl, mg and L. The L is the length of this pendulum, and we have from integral of sine theta from theta 0 to 0 angle. And the integral of sine is minus cosine, and from theta 0 to 0 it becomes minus cosine 0, that is minus 1, plus cosine theta 0. So if I put this integral into this equation, we have mgl 1 minus cosine theta 0. That is the work done by the gravitational force when it rotates from theta 0 to 0 angle. And if you take a look at this result, L times 1 minus cosine theta 0, that is, from this diagram, the length of this pendulum is L, and when there is a angle theta 0, then the length from vertical direction distance of this pendulum becomes L times cosine theta. That's by the definition of cosine theta. L times cosine theta 0 is the length from the pivot point to the position of this object. So the height difference between the theta 0 point and theta equals theta 0 point, 0 angle and theta 0 angle, that is L times 1 minus cosine theta 0, because this distance is L cosine theta 0, and this original length of this pendulum is L, so L minus L cosine theta 0 is the distance from here to here. So that is L times 1 minus cosine theta 0. So mg times L 1 minus cosine theta 0, if I rewrite L times 1 minus cosine theta 0 as the h, then that is the work done by the gravitational force for a free falling object by a distance h. It is equal to L times 1 minus cosine theta 0. So the work done by the gravitational force for this circular motion from one fixed angle theta 0 to the 0 angle is nothing but the free-falling work done on a free-falling object by a distance h. Distance h is L times 1 minus cosine theta 0. So in this case as well, regardless of this moving path, as long as the height difference is given by h, then the work done by the gravitational force is just h times mg. That is the work mg times h, which is L times 1 minus cosine theta 0. So regardless of this path, as long as the height difference is same, the kinetic energy or the work done by the gravitational force is identical. So that's the thing I like to mention. So that's the extra content related to the work and the force generating the work. That's about it.